Welcome to the Ex Terra Podcast. The Ex Terra mission is to explore and discuss the business of space and its effect on the national and global economy, as well as life on Earth. How does what happens in space affect your life every day? That's what we're exploring on the Ex Terra website, as well as on this podcast. My guest is Dr. Brian Kaplinger, Assistant Professor of Aerospace Engineering at Kansas University and Jupiter Project Officer at KSF Space Foundation. Brian, welcome to the program.
Hi, thank you for having me.
You study astrodynamics. That's a big, long $5 word. What is it?
Well, for starters, so astro as a prefix means space. And so dynamics typically refers to how things move. So as an astrodynamicist, we look at how things move in space. And so that's two different ways. One, it's how do you get from point A, point B, the trajectory of something, often called its orbit, that might be about a planet or another body. We also look at how something moves, rotationally. So in space, that's decoupled. For an aircraft or something like that, you might be used to the way that you're heading is the same way that you're facing. And for a spacecraft, you could be facing backwards, you could be facing the side. And so the way that you're pointing really doesn't matter. It's called the orientation or the attitude of a vehicle. So astrodynamicists study both. Some of us are really focused on trajectories and how do you get someplace. And some of us are very focused on attitude and how do we know which direction we're pointing and control it and things like that. And some of us like to look at both. So astrodynamics really covers all of those aspects of how things move in space.
What are some of the practical applications for those things? For instance, I'm sure that when you talk about docking two spacecraft together, astrodynamics plays a huge part in that.
Absolutely. So when you're talking about how things move in space, it's not always as easy as I want to point towards something and fire my engine and go there. So there's a classical problem that we have for undergraduate orbital mechanics that looks at the chase problem. This was something that came up in the Gemini program. And so if you have two spacecraft that are in an orbit together and there's one that's chasing or trying to meet up with the other, it turns out the actual solution is to slow down. And by slowing down, you enter a lower orbit, which moves faster. And so after one orbit, these two things can match up. So the way that things work in space can be counterintuitive a little bit and require different types of mathematics and equations to get figured out.
Now, you're serving as the Jupiter Project Officer at the KSF Space Foundation. What is the KSF?
So KSF is focused on helping to expand and democratize the base of people that are looking at using small spacecraft, whether it's for commerce or whether it's for science or whether it's for education. And so many of the customers are educational and they're focused on using CubeSats and other small satellite platforms to test things and to teach students, the interest about this. So KSF facilitates this by helping to do testing and helping to do design on these small satellite platforms. So they support balloon programs where you do high altitude ballooning to test whether or not things can deal with that type of environment. They do programs about designing. They have a nanosatellite engineering certification program in which they can certify that people, have learned how to deal with and build these types of satellites. And then the Jupiter project is focused on testing satellites, again, in high altitude, but also at high speeds. And so it's a rocket project that's focused on people that want to do that sort of high speed, high altitude testing.
And Dr. Kali Muhammad just unveiled the Jupiter project on Monday. He did talk about that with us on a previous podcast, but tell us a little bit about that project more in detail and your role in it.
Okay, so the Jupiter project is focused on trying to show a proof of concept for CubeSat testing with sort of small rockets up to an altitude of approximately 30 kilometers. So that's the target altitude for the project. The current demo altitude is going to be about 20 kilometers or more is what we're focusing on. And so by demonstrating that 20 to 30 kilometer range and then looking at larger vehicles that could do better, higher altitude and faster demonstrations, Jupiter is the first step, or the Jupiter 1 is the first step in pushing that boundary faster and higher. And so Essentially, the concept is a two-stage rocket made out of predominantly carbon fiber that is going to launch between 2 and ideally 3 CubeSats, depending on the mass of the system. And the customers would then be able to take measurements. We would be able to provide telemetry and any other testing that's needed at that altitude, and then they would be recovered safely on the ground.
How are the students at Kansas involved in this project? Are they helping to build the rocket? Are they doing the calculations for the experiments? What's the student involvement in that?
Yeah, so the students are involved in the design and construction of the rocket, and design is a multifaceted experience. And so from the very first, taking a look at a concept and developing that on paper, students are starting to do background calculations. They're starting to do the types of things you find in textbooks and saying, okay, it should be approximately this big, it should be approximately this diameter, it's going to go about this fast, and things like that. From there, we can move into the computer world where we have a little bit better modeling, and some of those equations are built in at sort of a simplified level. And so then they start to build the design into a slightly more refined concept where they're calculating aerodynamics, they're calculating the shock waves and where they're going to land, further downstream on the body. They're calculating how rigid the material is and whether or not it's going to be experiencing high stresses. So every subsystem of a vehicle like this, from the avionics, computers, through the structure, through the aerodynamics and controls and how it behaves, are aspects that the students have some sort of touch in affecting the design. So in looking at that design process, they then take what comes out of that and start to do more detailed analysis as to how it's going to be built. Now, the students are right now looking at constructing the primary airframe for Jupiter 1, which is basically a carbon fiber tube, but it's designed in such a way that it's going to handle a lot of bending stresses as we get really high aerodynamic forces that might deflect it from one direction or another. So if it goes slightly off axis, there's going to be a pretty strong force from the fins to try to correct that. And as that force experiences its way down the airframe, you get really strong stresses. And so some of the commercially available tubes and things like that, we don't have very strong confidence in based off of the numbers and data sheets that are available to us. So they're working on constructing some of that right now. Now, other parts of the rocket are purchased, but the students do a lot of background work in those purchases. They develop a set of requirements for what must this part be capable of doing. So if it's a computer, it needs to operate at this speed. It needs to not generate more heat than a certain amount. And so they develop that set of requirements as they build the design. And then they find the things that are commercially available that can satisfy those requirements. And then we acquire that through our purchasing, and then they would integrate and test those as part of the vehicle. So students are involved from the very early stage of the process through the end of the project, both as an educational opportunity, but also as a way to really make sure we have a lot of eyes on this and to make sure that there's nothing being overlooked in the final design.
How does that set them up then for a potential career in the aerospace industry?
Well, design problems are really interesting in that they hit every single aspect of what we're trying to educate into our students. When we're trying to educate into our students, we're not just trying to have them think about, what types of equations or things are going on. That's certainly a part of it. But we also want them thinking about how things are going to be built. So when they go to design, they want to build in things like tolerances, so something could actually be manufactured and still all the parts fit together. And then in the end, for a project like this, there's a customer, there's an interface and an integration. So they have to document and say how, the CubeSats or the test platforms are going to fit in here, how they're going to be secured, how they're going to be supported by the system. And so design is really interesting in that it allows students to do some hands-on work. It allows them to learn computer skills and modeling skills. It allows them to get some hands-on experience in the construction capability, but also in the laboratory and testing and data analysis side of things. So it really builds out and touches on all of the aspects that we're trying to educate into young engineers.
Tell us a little bit about your background and how you got interested in space.
Wow. Okay. So my background, I was born in Omaha, Nebraska. I went to Millard South High School, which is sort of in the suburbs there. And there were a lot of students in my school that were interested in space, engineering in general, and other things like that. So I think we actually have 4 aerospace engineers out of my group of friends that all went to different schools and things like that. And so we kind of spread out from there, but there was a lot of just coalesced interest. And I think a lot of that started with just shared interest in things like space flight, the shuttle program. Hubble telescope was very big at the time, and the images that were being released and the science that was being done. And so I really think a lot of us just took between that and interest in science fiction and things and saying, you know, this is really cool. These are tough problems. I want to get involved. I want to do some hands-on work. There's also a couple of astronomers and things like that, I think, that came out of that group of students. So I was sort of in that boat. I thought I was going to do astronomy. I wanted to be a scientist, big picture. But then when I got to school, you had astronomy and astrophysics type programs, which were very interesting. But they also had a lot of requirements that you do some deeper background. And I was looking at that compared to an engineering program, which there was less of that sort of well-rounded background, which I probably should have taken. There was a lot more hands-on work and opportunities to sort of get involved in projects like this that I'm doing with my students. And so I looked at their labs and their classrooms and the things they had going on and went, this is so cool. This is something I want to be doing. I want to be doing hands-on work and things like that. And so it just came apart from a tour when I was in college. I toured another department's facilities and went, wow, the things they're working on are so cool. And so that's why I think like the Jupiter project and other things like that are very interesting, is because they can inspire students that aren't even my students right now, right? We have a summer camp going on where there's high school students coming through, and they're going through my lab and they're looking through the windows and they're saying, what are they doing in there? That looks really cool. And so I like to imagine that one of those students is me, right? Looking at it and going, wow, I want to change what I plan on doing. So I ended up moving into aerospace engineering and got all my degrees at Iowa State University. And then I ended up teaching at Florida Tech University in Melbourne, Florida. And then now I'm at the University of Kansas here in Lawrence.
Should have stayed in Florida.
Yeah, so
I'm partial to Florida. It's where I live. So.
The weather was awesome. My family really likes seasons, unfortunately.
Yeah.
So that's my background. Now, how did I get involved in space? Again, like I said, it was an early interest. In this area, I specifically had a couple of professors and things like that that inspired me. And so I really liked the work they were doing, and I wanted to do similar problems. So I started working as an undergraduate research assistant when I was doing my undergrad. And then they started talking about graduate school. And I said, okay, that sounds interesting. I kind of want to stay in school. This is really interesting. And so I started working on some of that, which gave me the opportunity to go to conferences and present papers and things like that. And the people I met were just doing the most awesome things. And so I think from there, it was just a series of people and experiences that inspired me to take the next step.
I'm talking with Dr. Brian Kaplinger, Assistant Professor of Aerospace Engineering at Kansas University and Jupiter Project Officer at KSF Space Foundation. Take a moment right now and click on subscribe to make sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. Brian, some of your early work was on interception and mitigation of risk in near-Earth objects. And we all know that space debris is a huge topic right now, particularly with the number of satellites that are being placed in orbit. The risk of collision is very high on a lot of things. Are you still working on those issues?
So I'm not doing any active work at this point. I'm very interested in the scientific work that's going on with near-Earth objects. Now, as far as space debris goes, there is some intersection there. Most of the near-Earth objects tend to appear in families. Some of the families of near-Earth objects we think are larger objects that broke up at some point. And so there's this flux throughout the solar system of objects from small to large that are just zipping around everywhere. And at the speed that things are happening in space, that can be devastating for things like James Webb, as we saw last month. And so one of the problems with that is that our understanding of the risk is built around statistical models for how we think the likelihood is that there are so many particles of a certain size, or that they'll be passing through a certain volume in any given amount of time. And there's a lot of shared mathematics and modeling between the people that are trying to study the populations of near-Earth objects and the people that are trying to study and predict the populations of orbital debris. And the challenge there is a lot of that is not trackable. So we can't really get radar returns off of things that are too far away. We also can't return things that are in Earth orbit that are incredibly small. And so things that are difficult to be tracked are problematic for both issues, orbital debris and the near-Earth object population. So understanding general debris in terms of micrometeorites or human-made orbital debris is definitely a huge problem, and I think that they're very related. And a lot of the mathematics does go back to we don't understand the exact population of either. So when you have, for example, either satellite collisions that have occurred around the Earth, or for example, you've had anti-satellite weapons testing, they generate clouds of particles that we don't know what happens to them after that. And they could be moving relatively slow compared to the orbit, or they could have had very high initial speeds compared to the orbit of that initial object, and could find themselves in vastly different orbits that impact something that we don't know what's going to happen in the future. And so I think the challenge of this is that we should be able to have a better understanding of the near-Earth object population, or the micrometeorite population, so the very small set of near-Earth objects and rocks. And we should also gain a better understanding of what's going to happen with orbital debris, how we can help to mitigate that going into the future, and how we can try and clean up the area, as some researchers are looking at, and remove some of that debris from space.
But as an astrodynamicist, the scale and pace of the missions of satellites, particularly when we look at the Starlink constellation that's coming online, Kuiper, which is going to be a similar number of satellites, OneWeb, which is doing hundreds of satellites, that's got to be exciting. And yet, are we moving too quickly, or can that pace be improved?
So in terms of the types of ways in which we're using space, both as a society and also commercially to make money, I think it's a very exciting time. I think that when you have a lot of these projects going, you see an explosion in smaller companies and firms that are supporting that in terms of contracting to build out parts or to do research for components and ideas. And so I think it's definitely a very exciting time. Now, in terms of are we moving too fast? I don't think that I could ever say yes on that. But I think the question is, are we not moving fast carefully? And that I don't have all the information on, but I think that as an industry, we really should be thinking about, if we're going to move, explosively fast, can we do so in a way that is conscious of the other users of space, and where we're taking every step to maintain reliability and to maintain a system that works for everybody. So, for example, when you have vast constellations, those can be very safe constellations. Now, we have to think about things like the solar storm that decreased the lifetime on some of SpaceX's satellites in February. And, there's a couple of thoughts on that. Was it something that, they predicted there was this likelihood that could happen and they accepted the risk? Or was it something that they didn't do enough work on and didn't know that risk was as high as it possibly, could have been, given some changes there? And so they were operating on very, low margins when it comes to the lifetime of satellites. Now, that's devastating to well, it's not devastating, it's harmful to their bottom line. But in terms of the other problem, like we were talking about orbital debris, it's actually helpful. So there's a lot of these balances that occur in the space industry where we're trading one thing for another. If a company is operating really marginally when it comes to how long their satellite stays in space to accomplish its objective, they might not get as much utility out of it, and it might cost them money. But it also makes the orbital debris problem a little bit easier because you don't have these dead satellites that are floating around making life hard for everybody else. I think that if we have lots of satellites that are out there and they're all cooperative and they're sharing information about where they are, how fast they're going, they're, beaconing in the RF spectrum and things like that, so that we can have, like a space command and control type of thing, right? There's no unified version of that for space. So like in the FAA, air traffic control, where we're flying over a city and they're managing everything, there's nobody directly managing that in space. It's on the operators of the spacecraft. The Air Force does do tracking and send information out to people, but some of that's not exactly up to date, or it's not the best information. So I think as a community, one of the things we should start thinking about is some sort of information sharing database in which things like conjunctions where two objects might be close to each other are shared in near real time. And then the operators can talk about how they're going to opt to avoid that or mitigate that risk of a collision in a way that works for both of them. Because right now it's on both parties to figure out who's going to move, say if there was going to be a collision. Right. And some people may choose, no, the percentage, the statistical likelihood is too low, I'm not going to bother wasting my fuel to move. Or they both might move. Or possibly they might use more fuel than they had to, that if they had worked together. And so I think that as we have an increase in the population of satellites, we need to build out an infrastructure where people are talking to each other, they're communicating, they're sharing information. And so a lot of that can help everybody.
I don't know how familiar you are with aviation, but sounds like you're almost talking about what they call an ADSB system in the aviation world, which is where all of the little transponders in everybody's airplane talks to one another. And you can see in your cockpit what that airplane is, what its registration number is, how much higher or lower it is than you. I mean, it's pretty interesting stuff, and it's being used right now on aircraft. Sounds like that may be something like what you're talking about for spacecraft.
Yeah, no, I think it's a very interesting world. So the regulatory framework and who's responsible for what is very similar between the aviation industry and the aerospace industry. Even in aviation, though, there's sort of two general operating modes. So you have this operating mode that is performance-based regulations, and then you have an operating mode that is very prescriptive directionality. So if you're a small aircraft pilot or a general aviation pilot, then, one of the strictest maxims is just, don't harm somebody else's asset or aircraft or things like that, right? And so it's still sort of on you to avoid a collision. If you see another aircraft, and you're just at low altitude in unregulated airspace. Now, if you're near a city or something like that, or you're part of a bigger, jet platform, then there's an air traffic controller that's telling people, okay, the best way is for you to increase altitude, go up one flight level, and you're going to go down one flight level, for example. And so there are some crossovers between that. The difference is that in the space world and the world of potential satellite collisions, that there is no air traffic controller. There's people right. that are sending out that information via, two-line parameters for, what your orbit is. And there are some people that are sharing collision possibility and conjunction information. But to my knowledge, it's mostly people that are independent operators figuring out whether or not they need to take action to avoid a collision.
Let's turn the corner a little bit, because you did a conference paper with Buzz Aldrin. Talk about that just a little bit, and how was it to work with Buzz?
So Dr. Aldrin was absolutely a fascinating person to work with, not just because of the history, but because when I talked with him, he had all sorts of ideas, and his mind was still incredibly sharp, and he could just jump from concept to concept. And as somebody who had a deep background in the area, I followed along with him. And so I was like, oh yeah, and then this, and then we could do this other thing. And he goes, oh yeah. And so he would pick up from that thread and come up with another idea. So he still really understood his orbital mechanics and has been studying it for decades, really, and had some really good ideas for, what other things or what the impacts of an idea or a concept would be. And so I thought it was absolutely fascinating to work with Dr. Aldrin, simply because, he demonstrated to me that he's more than just, this person from history who did these awesome things. He is still an incredibly intelligent individual who still has that background, who still knows what he's talking about when it comes to orbital mechanics. And, it really was a very humbling experience.
What was the gist of the conference paper? What was the topic?
So the topic of that paper was on cycler orbits. And the idea of a cycler orbit is for some sort of human mission to Mars, the moon, or another planet. The idea is that once we get past the flags and footsteps sort of exploration, we're going to start to have, scientific outposts that are permanently housed, similar to what we have in Antarctica. And then we're going to start to have, sort of pre-colony type of activities. And once we do that, it's going to be less important of what the cost of, getting people there and back is for one mission. And as it become more about what the marginal cost of getting a set of astronauts to and from, say, Mars and back to Earth might look like. And so when you're trying to figure out ways of minimizing marginal cost of a human space mission elsewhere in the solar system, one way to approach that is with something like a cycler orbit. So a cycler orbit is an orbit that connects the orbits of, for example, Earth and Mars, and it is periodic. And so, well, all orbits are periodic, but it's periodic with respect to the synodic period of Earth and Mars. So the relationships that you have, the encounters with Earth and the encounters with Mars, are something that keep recurring. And so the idea is you basically have sort of like a bus or mass transit system. We called it sort of like a cruise ship model, in which you have this large vehicle that has all the things that humans need to stay happy and healthy in deep space. It has shielding, it has food, it has water, reclamation systems. It has things that can help astronauts maintain their body strength and their bone strength and things like that. All these things that are very heavy, and you would get them up to speed by launching from the Earth and boosting it once. And these are things that would be similar in size to the International Space Station. So they're very, very heavy, hundreds of tons. And you would do that once. And then you would have smaller vehicles similar to the Orion capsule or similar to like the Apollo capsule that are meant to hold humans for a few days at a time. And those would be very light. And then you could send humans in the smaller taxi vehicle up to a cycler. You could hang out there for the long duration of the flight. And then when it encounters Mars, you would hop off, enter Martian orbit, and then go on to do your mission. And then you would reverse that on the way back. So this paper with Buzz was looking at ways in which we could operate that sort of Earth-Mars human exploration infrastructure by looking at the orbits that could be useful for that. And there are some in which you could do it both directions, both to Mars and back, and that's what we were looking at.
Brian, we are just about out of time, but we ask all of our guests this kind of last question, and that's to look out, if you will, over the next 10 to 15 years and tell us what you may see coming in the realm of space commerce.
Space commerce. Okay. So
yes.
In space commerce, it's a very, very interesting time. You have a lot of new entrants into the traditional launch world in competition. We have a burgeoning small launch industry that are looking at launching a few hundred kilograms at a time, or even dedicated CubeSat type vehicles. And so as part of all of that, you also have subcontractors and you have people looking at technologies and people looking at democratizing the group of people that are building subsystems, attitude control systems, electronics, things like that. And so it's a very exciting time to see all of that. It's also exciting to see people like SpaceX and Blue Origin pushing into heavy launch, which I think is absolutely critical to the next steps in both space research, but also in space commerce and making near Earth and cislunar space sort of functional part of our economy. And so I think it's very exciting. It'll be interesting to see what happens. Some of these companies will not continue to be working in 10 to 15 years, but I think some of the best ones will still be around. Will be thinking of their next big ideas. And so it's really interesting to enter this time of competition and to see who's going to win out. And hopefully we have multiples of them that win out and can continue to make space easier, faster, cheaper, and to reach for the best things that we possibly can.
Sounds great. And a goal we can all aspire to, I think. So thank you very much, Brian. We are out of time. So really appreciate you being with us today.
All right. Thank you for having me.
Dr. Brian Kaplinger is Assistant Professor of Aerospace Engineering at Kansas University and Jupiter Project Officer at KSF Space Foundation. And that's going to do it for this edition of the Ex Terra Podcast. You can subscribe to the audio version of the podcast on Spotify, Apple Podcasts, and many other popular podcasting platforms. Be sure to click on subscribe so that you don't miss an episode of the podcast or any of our other videos. You can also get daily space commerce news at xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on Twitter at xterrajsc. Until next time, I'm Tom Patton. Thanks for joining us.